So this is joint work with Pavel Hrubes and Shai Moran and Amir Shpilka and Amir Yehudayoff. And what are we discussing here? So the fundamental result in statistical learning theory is the equivalence of packed learnability with the finiteness of the Vapnik-Chevronics dimension. That's kind of the basic of from the 70s of statistical learning theory. However, this very clean result, it applies only if your task is binary classification. And the question is, can we similarly understand combinatorial colorization that will tell us when classes of more general functions, not necessarily binary, will be learnable? And so we were looking at this and we got the surprising result that this is independent of set theory. So that's what I will try to explain here. So what are we going to do? So I introduced a general learning problem, a more general than just binary classification. We call it EMX, expectation maximization. And then I will introduce the notion of a sample compression scheme, which is a tool that translates a statistical learning problem into a combinatorial game. And we can show the combinatorial game is equivalent to the learnability. Then we will show that this combinatorial game, whether it can be decided or not, is independent of set theory. So we will conclude that the Emacs learnability is independent of set theory, and therefore there can be no dimension that characterizes it. So that's the plan. Okay. So what is this general learning problem? So let me start with the usual learning problem. So you have a collection of real-valued functions, queries, and you have a sample from an unknown distribution, and you want to estimate the expectation of those queries. So say you have some kind of hypothesis, or you have all kind of possible settings of parameters to a deep neural network, and you have data, and you want to know how well they fit the data. So each of setting has an expected loss, and the classical problem is how many samples do I need to be able to estimate the losses of each of the settings of my neural network. This is well understood, and this is called uniform convergence. However, in many applications of machine learning, you don't really care about estimating each possible setting of the parameters. So you have a collection of potential functions or potential models. You see a sample from an unknown distribution, but rather than trying to estimate the loss of each of them, you just try to find one model that will be close to the best possible on expectation. So this problem is, on the surface of it, simpler than the uniform convergence, which is characterized by the visit dimension. So rather than being able to estimate the loss of each model, you just want to find a model whose loss is close to the optimal based on a finite sample. Okay, so this is how we phrase our problem. And it turns out that many learning problems can be cast in this setting. So binary classification prediction, you want to find the best binary classifier. You don't care about the loss of each of them. Multi-class prediction falls into it. Case-center clustering problem. So you say you have the collection of all potential locations of case centers, but you don't want to estimate the loss of each of them. You just want to find a location whose loss on expectation will be close to the best. So there are many learning problems, linear regression, that can be cast in this general setup. Rather than caring about estimating all the models, you just want to find a single model that on expectation with respect to the probability distribution that generated your training sample is close to optimal. So that's a very general learning problem. Now, how do we handle learnability in general? So packed learnability was introduced in the context of binary classification, and it was shown that you can always do it by empirical risk minimization if you just care about sample complexity. There is weak learnability, which is equivalent to packed learnability. The uniform convergence, as I mentioned, is a purely statistical notion, and the existence of sample compression schemes. So all those are tools, and finiteness of the visit dimension. So all those are tools that were introduced to understand statistical learning theory. And in the binary case, the fundamental theorem of statistical learning says all of those are equivalent. So a class is learnable. If you go back, a class is Pak learnable if and only if it's learnable by a period minimization, if it's and only if it's weakly learnable, if and only if the visit dimension of the class is finite. So all of those 6 or whatever different statements of the problem or characterizations or descriptions of a class are all equivalent, but this is for the binary case. So in 2010, in work with Amit Danieli and Sivan Sabato and Shai Schwartz, we were trying to see what happens when you want to predict just not 2 binary labels, but say you have a larger set of labels. Does the same characterization still hold? And then we found that in that setting, it could be that some ERM algorithm learn well and others fail, which immediately implies that extending this nice characterization of all of the things that are equivalent from binary to multi-class to multi-labels fails. So and that raised the big question of how to characterize a more general setting of learning. So what I will do here, and the question was raised in 2010. We don't have a full answer for that yet, for this specific question, but the more general notion of learning is what we analyze in this work. So I will focus for concreteness on a very simple case of this model. So assume that you have some domain space X, and H is a collection of subsets of the domain. And you have an unknown distribution, and the EMX for X is find a set H in your class whose probability weight is close to the maximum weight of all possible H's in this class. So you have a collection of subsets, you have an unknown distribution, you see a sample, and you want to find out a subset in your collection that has weight close to the optimum that you can get with respect to this unknown distribution. That's the concrete Emacs problem. And we can easily see that already the classification, already things break down compared to what we know for Pak learnability. So let H be the class of all subsets of some infinite domain. So uniform convergence fails. I mean, based on a finite sample, I cannot estimate the probability of hitting each subset. I will always overfit. But on the other hand, if all I want is to find one set that has the maximum probability, that's trivial. If I have in my collection all possible subsets of domain X, I want to find a set that has maximum probability of being hit, I will say it's all of X. So we see that the Emacs is solvable when the visit dimension, but the uniform convergence fails. I cannot estimate all of them, but I can easily tell you who will have the largest probability. So it shows us that uniform convergence is indeed weaker than a more demanding requirement than Emacs learnability. So our goal is to characterize, figure out which classes are Emacs learnable. And furthermore, can we find a purely combinatorial characterization of these classes, like the visit dimension characterizes binary classification? So I want to say something about compression scheme. Compression schemes were introduced by Manfred Warmuth and Nick Littleton in '86, and for sample compression for binary classification. So I'll just give an example. Assume you get labeled points which are colored according to whether they are inside an unknown square or outside the square. And you can somehow compress all the information here to just picking the leftmost, the uppermost, the rightmost, the bottommost point. If you just give these 4 points to someone else, they will be able to label the sample as well as they've seen all of the labels. So that's called sample compression. It's introduced by Manfred Baumont and Ilston in '86. And they showed that if you have compression of a class, then it's learnable. And 30 years later, Moran and Yehudayoff, which are co-authors of this paper, showed that this is also a necessary condition. So the existence of such a compression and PAC learnability are equivalent. But that's for binary classification. So now we want to come up with a compression tool that will capture the Emacs learnability. So for the Emacs learnability, we defined a generalized notion of compression. I put it in kind of I don't want to get into technical details. Rather than repeating the definition, I'll just say that we could show that this compression is equivalent to Emacs learnability. And I will demonstrate this compression on the case of a collection of subsets that you want to find which subset has the maximum weight. So again, now to make the problem interesting, you have some space X, but your collection contains all the finite sets, only finite sets. And now what will be the compression? So it's a game. Alice gets some finite set S of points from this. You have an unknown probability distribution, but we are talking about just a combinatorial game. Alice gets a set S and has to pick a small subset S prime of S and send it to Bob. And Bob has to compute, based on the small subset S prime, a finite subset of X. And the goal is that to find a strategy by which for every S, Bob can figure out a superset of S. So let me demonstrate it with some examples. So we ask, can they settle for a bounded size as S prime? So the answer depends on the cardinality of X. So if X is finite, then it is trivial because Alice doesn't have to send anything to Bob. Bob will just output the full X because he is allowed to output any finite set. So Alice got a set S, Bob gets only a small subset that she picks, and he has to find a superset of X. So of this set. If X is finite, it's easy. What happens if X is countable? So think of a natural numbers. Alice gets a finite set of natural numbers. She wants to send to Bob only small few of them, and Bob has to come up with a finite set of natural numbers that contains Alice's set. So in the natural numbers, it's very easy. Alice gets collection of natural numbers. She will send the maximum number. And Bob will send this initial segment, which contains the set of Alice. So Bob saw only the maximum sample point for Alice, and he could recover a superset of what Alice saw. So it's very easy for countable. But it gets interesting when X is uncountable. So again, this game is equivalent to the Emacs learnability. It's a very simple game between this Bob and Alice. What happens with X is uncountable. So I have to tell you something about cardinalities. So Alephs are the sizes of cardinalities of infinite sets. Aleph 0 is the cardinality of the countable sets, the natural numbers, the rationals. And each Aleph n plus 1 is the first cardinality which is larger than alpha n. So in set theory, we know that there's always the first larger cardinality. And Cantor theorem states that the cardinality of the set of real numbers is larger than Aleph 0. But it doesn't tell us how large in the ladder of Alephs, how far up are the real numbers. So Paul Cohen in the 60s proved that the axioms of set theory cannot determine which of the larger cardinals is the cardinality of the real numbers. Is it Aleph 1? Is it Aleph 2? Is it Aleph million? We cannot determine it based on the axioms of set theory. Now back to our game between Bob and Alice. So it turns out that for every X, for every K, if X has a size smaller than Aleph K, then Alice can settle for sending at most K points. So if they're playing this game, you see there is some domain set, very big. Alice gets a finite sample. She wants to set Bob subset of a finite size, and Bob has to recover a finite superset. She can settle for at most k points if and only if the cardinality of the domain set is less than aleph k, which is, it's pretty amazing because it's a completely finite game and it characterizes infinite cardinalities. Now we can go back to our problem. We said that this compression, existence of finite compression, is equivalent to Emacs learnability. So Emacs learnability turned out to depend on the size of the domain in the Aleph hierarchy. But we don't know what is the size of the reals in the Aleph hierarchy. So the corollary that if for every finite k, the cardinality of the reals is larger than Aleph k, which is possible by what set theory can prove, then there is no monotone compression. So if we go back to our learning, I mean, I don't know if I have time for the proof. Probably not, right? Chris, how am I doing?
If you want time for questions, you have like 3 more minutes.
Okay, so I will not get into the proof. So we can prove that this is a very nice characterization of the Alephs by a finite game over finite sets, if and only if. And so you have a monotone compression of size k, if and only if the domain is of less than Aleph k. And now we can get to the connection to learnability. So we said that the existence of a finite compression scheme H is Emacs learnable if and only if it is weakly learnable, if and only if there is a finite size compression scheme. So now, if we go back to the equivalences, we see the equivalences we had before. The blue, the ones that remain. Learnability, Emacs learnability is equivalent to weak learnability. It's equivalent to sample compression, but even quantitatively, every class has a monotone compression of size logarithmic in M, if and only if it is learnable up to a precision a third in the Emacs model with M many examples. So we have a total equivalence between this game, how many points Alice has to send to Bob, and the sample size needed for Emacs learnability. Once we have this equivalence, we can say that if we look at the set of all finite, collection of all finite sets, we want to learn it, Emacs learn. So you have a distribution over X, you want to find a finite set that is close to the highest weight according to this distribution. You can do it if and only if the cardinality of the real numbers is less than Aleph omega. Aleph omega is the limit of the Aleph case. Aleph 1, Aleph 2, Aleph omega is the limit. So this collection of subsets, finite subsets of the unit interval is learnable if and only if the reals are less than Aleph omega, which we know is independent of set theory. So with this connection between the 3 components, we got independence results for a very basic learning task. Just find the set of close to highest probability with respect to an unknown distribution based on a finite sample. So we can even give a quantitative version. And right, so since the cardinality of the reals can change using forcing, I mean, we're not cheating here. When we change the cardinalities of the reals, we don't add reals and we don't add finite subsets of reals. So our domain stays the same, the collection H stays the same, but the learnability changes between one model of set theory to another model of set theory, and therefore it's not determined by set theory. And so the Emacs learnability of the class of all finite subsets of the unit interval switches between being learnable and not learnable depending on extensions of set theory. So it is impossible to either prove or refute that it is learnable. Okay, what about existence of dimension? We wanted a dimension that characterizes this general learnability. So we have to define what we mean by dimension. So we have a precise definition of what we need by combinatorial dimension, but we see that this combinatorial, here is the definition, I won't have time to go into it, a combinatorial dimension of finite character by a logical formula. And anyway, all the dimensions that we are familiar with in machine learning, statistical learning are of that nature, but if we change a model of set theory, such characterization will not change. So if we had a dimension, the dimension will be the same in all models of set theory. Therefore, no dimension can characterize its learnability, because the dimension will stay the same, but the learnability will switch depending on what is the cardinality of the bits. So one interesting conclusion is that don't search for a dimension for general learnability, it doesn't exist. You will never be able to prove it. So there is no finite character notion of dimension that characterizes this important Emacs learnability, which is actually what we care about in learnability usually. We just want to find a set that minimizes the loss or maximizes some objective. Okay, so that's our nice corollary here. Where this independence comes from? I mean, you see, there was nothing in definition of learning. When can independence come into the game? So it turns out that it comes from the notion of sample complexity defined in terms of functions. There is a function. What does that mean? A class learnable. So Vaptik and Chevonenkis and Hausler and Varmuth, all the Valiant, of course, all the pioneers of machine learning, they were talking about a function that takes samples into a prediction. But functions are too difficult objects. If instead we talked about algorithms, learning algorithms, we would not have this independence. So, because they're programs. And usually we do want to learn programs. So in a follow-up work with my students, Sushant and Nivasini and Tosca and his colleague Hrubes, we redefined learnability in terms of algorithms. We said a class is learnable if there is a program that can take you from samples to predictions. Very natural. But it turns out that once we do this step, the characterization by VC dimension breaks down. Everything we know about learnability, we don't have any theorems anymore. So that was in ALT 20. I think it's a very interesting direction. Of course, we want learnability to be defined in terms of programs that learn. But once we do this step, the nice characterization by finite VC dimension no longer holds, and we are again on a white page. So that's where we are, and I really encourage you to look into this problem and to the papers. Thank you very much. I'll be happy to take questions.